The next presenter will present one of the most important updates in the ecosystem. It's the Fate Virtual Machine. He will tell you about its security and its benefits in comparison to the previous version of the virtual machine. He's been programming since 1980. That's like, how many years is that? I don't know, I'm not gonna count. That's too long, that's too long. He's behind one of driving forces behind high-performance selling project. And in his PhD work, he implemented an effective native code compiler, compiling the Erlang AEVM code to the native machine code. Currently, he's working on the core of aeternity, so please welcome Dr. Erik Stenman. A round of applause, thank you.
Thank you. So I'm going to talk about the new virtual machine, or transaction engine as we call it, to get the nice name Fate. Mostly that's the reason. So as with the design of the new language, Sophia, the main focus has been on safety. But first, a little background about the team. So we have been a couple of people working now for, well, since January or February, basically we started on the new version of the virtual machine. So it's me. I've been programming for a while, as was mentioned earlier. And 10 years of this time I've been working with virtual machines and programming languages and language design and implementation. And after that, another 2 years now with Eternity. I have written a book about Beam, the virtual machine for Erlang. That's free on GitHub if you're interested. But it wasn't only me in this team. We also had a lot of other great people like Tobias, who is the main author of Dialyzer, a great tool for Erlang, and also member of the high performance group at Uppsala University, where we implemented faster versions of Erlang back in the days. And Hans, who has been working on the language. And also Ulf Norell, who is not here today, but he has been implementing programming languages for a long time, and some really interesting complex languages, and he has done most of the work on the Sophia compiler, also on the virtual machine and so on. And Thomas Arts, who I think will be speaking a little bit later, has focused a lot on testing of this virtual machine. I think he will talk a little bit about testing later also. So it was really a great team that we got together to work on this. And as I said, the focus was really on safety, but I think we also achieved a little bit in the way of efficiency with this new virtual machine. So the name is Fast Eternity Transaction Engine, or Fate. So since the goal was to make the virtual machine safer, we started to look at things in the virtual machine of previous versions of virtual machines that could be problematic. So one thing is memory addresses. That's usually something that can be very complicated if you can have pointers to memory and pass them around, and suddenly they can start mean different things in your program. So we don't have that in Fate. And we have built-in data types, so it's a typed language, and we have built-in data types, and we'll talk more about this in a little while. And also it's built specifically for Eternity, so there are a lot of high-level operations working directly on the chain or the state trees in the machine. Also, in the virtual machine, it's not just, as I said, just memory, and also with the code, it's not just memory. We actually have functions, and they have type signatures. So they have a type, and they have a name, and this is part of the machine, not just part of any language that you put on top of the machine. So it's typed, and we have a lot of nice types in Fate. For example, the integer type is unbounded, so you can have arbitrary sized integers. If you want to find out what a million raised to another million is, you can do that. It will probably cost you a lot of gas, but if you have that gas, you can keep on calculating that big numbers. We have booleans that are true or false, and it's not just like sometimes it's 0, sometimes it's 1, sometimes something that's not 0. There's only true and false, and it's a specific type. You cannot use an integer in an if statement and say, if this integer, you have to use a boolean. And we have some chain-specific types, like addresses, contracts, oracles, oracle queries, and channels. And when we extend the aeternity chain with new features, there will be more types like that added to the virtual machine also. We have strings, so these are byte arrays. Then we have bytes, which is also byte arrays, but they are of a specific size. So you can have a byte array of 8 bytes or a byte array of 16 bytes or whatever you want, but it will always have that length. And then we have some higher constructors. I'll talk a little bit more in details about that. We have bits, which is a infinite bit pattern. So if you want to keep a lot of flags for some reason, you can use this bit pattern. And you can also start with the bit pattern which has all the bits in the universe set to 1. Or you can start with a bit pattern of a certain size with all 1s or all 0s. So that's very nice. And then we have one more type, which is a type representation, so you can talk about types also. So the built-in constructive types are tuples. So tuples are sort of like a list of values, but it's of a certain size, and every element in the tuple has its own type. So you can have the empty tuple, or called unit in Sophia. You can have a tuple with just one element of one type, like an integer or a boolean or whatever, but it always has that type. Or you can have a tuple of several values, which each of them have a specific type. We have lists, so you can put together a list of the same type. So you can have a list of integers, for example, and then you can just add elements to this list and traverse the list. And then we have maps that are key value store. So you have a key of one type, and you have values of another type. And there's a restriction on map that a map cannot have a map as a key. And this is because if you put maps in your state, these structures are mapped in a different way to the state, so that you can actually, you don't have to read and write the whole map from the state when you're working with the map. But it will be efficiently calculated by the virtual machine at the end, whatever updates you have done to your state, and you will only read the elements that you access. But you can have local maps also in your program that are not in the state, and keep track of things. And then you can make your own types, basically, by having variant types. So the variant type, you define a number of different versions of the type. They get a tag, so you can have a variant type like optional, which can be none or some integer, for example. But you can define arbitrary variant types. And they have they are sort of like, each variant is sort of like a tuple with a number of typed elements. So Fate is designed for Eternity, so it also has some data types that are directly Eternity things on the chain, like address, contract, oracle, query, and channel. And also there's a lot of instructions in the instruction set of the machine, not like primitive operations that you have to do a call out for or anything like that. Or so there are instructions in the machine set, and they are in the reference implementation. They are very closely linked to the actual implementation of these things that you would use for other transactions in the node. So they're using the same code with even less overhead from the virtual machine to do these things than if you do it from a transaction from the outside. And Fate has, as I said, functions. So in the EVM or the AEVM, for example, code execution always starts at address 0, and you have a code address space, and then you, at address 0, you start to figure out what function did you really want to call. So you do this by switching through the different functions that exist and then jumping to the right place and doing whatever you want. But in Eternity, we have functions with types. So you know that the argument to this function should have a certain type, and the return should have a certain type. And this is checked when you try to call a function. You can directly see whether you're calling it with the right arguments. There is also a flag that you can set in the on each function in the machine, whether it's payable or not. So if it will accept if you try to transfer tokens in the call to that function. There's other flags also, which is whether it's a local function or an exported function. So if you have a local functions, there's no way to call it from the outside, from other contracts or from a transaction. It can only be called from other functions within the contract. So on the top level in the code, there's functions, and they have a name, and when you start executing, it will find the right function and go there. And there's still no code memory with addresses. Instead, a function is made up of basic blocks, and each basic block is made out of a list of instructions. So there's no way that you can jump to the wrong place in the code, because there's only basic blocks, and as soon as you in your code introduce some type of branching or jumping, there will be a new basic block. So the basic blocks are defined by the instruction stream, so there's no way to make a mistake in creating your basic blocks. So there are actually no markers in the code where a basic block starts or ends. It's only determined by the instructions in the code. And they are just a sequence of instructions, but when they are turned into the machine, they will become this map of basic blocks. And of course, there's no way to write to this code memory, so you cannot change the code while you're running. There is no word size in Fate. It's not even specified, the word size. So it's up to the implementation to decide what word size to use. But for example, for integers, you should be able to have any size of integer that you want. And in the current implementation, It's using Erlang in the back end, and it's going to use the smallest possible word size that's needed. If you're running on a 64-bit machine, it will be 64-bit word size in the implementation currently. So there's, as I said, also no memory addresses that have different size that you could make mistakes on reading too much or too little from memory. You get the whole data type all the time in Fate. Instead of memory, Fate has what we call variables. So each variable is a storage slot where you can store one Fate type. And they are local to a function. Again, there's no sizes on these things. And a variable doesn't have a type. It's just a slot where you can store something. But the thing that you store there will be tagged so that there's no way for that thing to be of any other type than the type it's supposed to be. So it's a Boolean, not, and if it's integer, and if it's integer 0 or integer 1, you cannot think that it's the Boolean true or false or anything like this. There are special type of variable that has a negative name. And that is a mapping to the state. So if you read or write to a negative variable, you read and write to the state. But this is done also in an efficient manner. So when your contract finishes, it will figure out what to actually write back to the state. And when you read, it will read it whatever, only the things that are needed. And maps are handled, as I said, a bit differently. So they are stored separately in the state tree, and you only read and write one key value par from the map. Currently, the Sophia compiler puts everything in the state except for a map into just one state variable in Fate. But there's a possible future compiler optimization to spread this out on more state variables to reduce the size of the state that you need to load and write back. But since the thing where you store, there's potentially store a lot of data would be in a map, and this is efficiently handled already. So finally, let's look at small example. Here is some Solidity code and some Sophia code for the same thing. This is sort of the simplest thing you can write, a contract that has a function that returns the integer that you call it with. In Solidity, it's in this case, it's a 256-bit integer. In Sophia, it's an integer of infinite size. So this is the assembly code of the Solidity version compiled to the EVM. So this is just to get a function that returns the integer that you call with. In Sophia, we can compile to the AEVM. It's basically the same, so it's a little bit smaller in Sophia contract compiling to AEVM, but basically the same. But if you compile to Fate, the machine code becomes this. So we're a little bit smaller in machine code. We can look at it a little bit bigger. You can actually read it. There's a function, there's the init function, so except for the compiler automatically adds an init function to your contract. There's comments here for where the basic blocks are. You can store comments as annotations in your bytecode if you want to, but you can also strip them away. They are not needed for execution, but there's a way to store comments in your bytecode actually, so you can get debug information from your compiler all the way into your machine. And then there's a main function. It has a type, integer, and it returns an integer. And all it needs to do is return the argument that it's called with. So a little bit shorter and easier to read. In fact, we're 9.6 times smaller, or AEVM contract is from the same Sophia compiler is 9.6 times larger than a Fate contract. Or it's basically 10% of the size for a Fate contract compared to a AEVM contract. To summarize, Fate is safer. We have types, we have structured data, we have arbitrary sized integers, and it's more efficient. 9.6 times larger for AEVM. It's cheaper, lower gas costs. There might be a little bit tuning, so I'm not going to say exactly what this will be in the release, but definitely cheaper. And it's basically 3 times faster to execute the same Sophia code on Fate than in AEVM. So that's it.
Thank you. Thank you. What time is it? Yeah, okay, let's have one question. So, who has a question? Come on. Okay, I see one. 1 second. There you go.
So my question is about the basic blocks. Are the basic blocks defined at compile time or at execution time?
At execution time. So they are defined by the instructions in the instruction stream. So in the code that the serialization of the code, it's just a series of instructions. And when you load it, you will find the basic blocks.
Okay, so there's no way to manipulate it at compile time?
No. But of course, you can make the mistake of then trying to jump to a label to a basic block that wasn't the basic block that you thought it would be. Yeah, there's...
So you can confuse people by putting comments?
Yeah, you can confuse them by putting comments, but that say some other basic block, yes. There's actually a feature of the pretty printer that finds the basic blocks and prints the comments for you. So the comments are generated by the pretty printer. So if you're using the standard pretty printer, you get the basic block structure just to be able to debug your code. But of course, if you put your own comments in there and they say crazy stuff, you can fool people.
Thank you.
Right, thanks. Another round of applause, I think, for the speaker. Thank you.